Okay, next setup is section 2, Newton's second law for a system of particles. So this is an expansion of the ideas before. It's a pretty short section, but it's pretty nifty to see the applications. So the center of mass of motion is going to continue unaffected by any forces internal to a system. So for instance, billiard balls. Any collision between those billiard balls or pool balls could be internal forces, and the overall center of mass should be the same. And we'll see some video clips in just a moment. So in other words, in terms of Newton's second law, the motion of a system's center of mass could be described as the net force is equal to the total mass times the center of mass of the system of particles, which once again you could break into x, y, and z components. So a few reminders, F net here is the sum of all external forces. So our system is not just one object because it's more than one object. We have to sort of draw our circle and only consider forces that are outside that system. M is the total constant mass of this closed system. So keeping that all the same, and A is the center of mass acceleration. So based upon the center of mass motion equation, we could consider some examples. One is a billiard collision, right? So hopefully this is properly displaying, but the cue ball, the white one, struck, and it passes through and knocks into the others. But all those forces of them knocking together are internal forces to the system of all the billiard balls. So that means the net force acting on them is 0, and the net acceleration is 0. The center of mass will travel at a constant velocity. And if you could sum up all these individual motions, you'd see that overall, the center of mass continues moving in the same direction as the cue ball, minus some reflections off the walls. Right? The only external force here is when the cue ball is initially struck. Okay, another example could be a baseball bat, right? Where A is equal to G, so the center of mass should follow a gravitational trajectory. So if you fling it across the room, you should see that. I couldn't find someone throwing a baseball bat, which is probably better, but I did find these military individuals who are throwing a rifle, which is even cooler than throwing a baseball bat. You see the one in the front flings it backwards, and even while it's spinning, it follows that gravitational trajectory. It follows the arc across the way. If these aren't displaying properly in the screen share, please check it out in the slides yourself, because it's cool to see. It's amazing it can do that. They're using physics, right? That's what it all comes back to. And the final example is going to be an exploding rocket. So for an exploding rocket, all the explosion forces are internal, so only the gravitational force acts on the system, and the center of mass will follow a gravitational trajectory as long as air resistance can be ignored for the fragments. Air resistance will make it more complicated. So I found this cool GIF of some sort of ballistic that is exploding, right? And you can see all the pieces continue traveling in the same direction, right? It's not that the center of mass has changed. They spread out, but they're still following that same forward center of mass. Or a depiction of it from our book shows a rocket being launched off a cliff, and even though it explodes partway, all of the pieces overall will still follow that same trajectory. So it still balances out. So this is where center of mass and Newton's second law can help us to understand and explain some interesting scenarios. And that pulls us through Newton's second law. Next time we'll take a look at linear momentum. So, see you soon.